Okay, good afternoon and welcome to my vegetation class. This vegetation class will cover chapter 5. Chapter 5 is actually some application of Newton laws. And as I said, always, if you have any question about vegetation class, you can send me email by using this email address, or you can write me on Canvas. Let's start with the first question. First, simple. Yes? Okay, start with the first question. And you have two forces and you have a mass. This mass is given with 3.1 kilogram. And this mass undergoes acceleration. Acceleration vector is given with this one, 0.95 I in x direction. And also it has a y direction component, 0.32 meter per second square, of course, unit of acceleration. If one force is this one, this vector, what about other one? And it's simple, as I said, application of Newton's second law. What was Newton's second law? F is equal to ma. M here, mass of your object, A here, acceleration, both acceleration and a force are vectorial quantity here. Okay, acceleration, of course, the unit is here meter per second square, and mass unit is kilogram, and the force unit in this case will be Newton. Okay, for this question, mass is given in the question as 3.1 kilogram, right? Acceleration is given this vector, yep, and you will find that this force here, but this force actually resultant vector of two forces. One force is given here, you will find the other forces. We can write down like this, F1 plus F2 equal to this force, okay? And you know this one is here, and you will find this F2 here, okay? So let's go to solution here. As I write down here, F net will be equal to F1 plus F2. You have two forces here, will be equal to MA from the Newton's second law. Okay, in this case, if you rearrange this equation for F2, because you want to find the F2 here, F2 will be equal to MA minus F1, right? Okay, so after that only you will put the numbers here. F2 will be equal to MA minus F1. Your M is 2.1 kilogram, okay? And here is the acceleration, right? So this is your force one. And when you do this calculation, this will be your force two, okay? Force two vector is here. If you want, you can calculate the magnitude and the direction of this vector, right? Maybe you remember from the previous class. Please do this on your own. Calculate the magnitude and the direction of this force, okay? Any question? No? Second one then. And you have a setup like that, you have a two inclined plane like this, you have two way here, and the two masses you have, and left hand slope angle is given with 64 degree. This is 64 degree, okay? And what about this one? Right hand slope is given 26 degree. Oops. How should the masses compare if the objects are not slide is important here, along the frictionless slope? You don't have any friction here. First of all, to solve this kind of problem, you should draw free body diagram of your object in the question. And for this question, you have two objects. One is this one is this one. Okay, so free body diagram for the object will be like this. Of course, I will show you what is what here. Okay, And let's start. This one is 64 degree for the left mass, okay? You can draw a coordinate system along this rope, and this will be x direction, okay? And the normal to the surface will be your y direction, okay? You can easily see the x direction, dotted lines shows the x axis, and the dotted line here shows the y direction. Here is the point is your mass here. In free body diagram, you are showing all forces exert on your object, okay? So you can easily see from here, in x direction, along the x direction, you have a tension, right? You have a tension. Let's denote this tension as T left, tension on the left mass. We are denoting as TL, okay? This is mg, okay? This is weight of your object, okay? Like this, okay? You can easily see from here, your mass, because of this inclined plane, has two components, this one and also this one, okay? Okay, and of course, because of the third laws of Newton, action and reaction, you have a normal force along the y-axis, right? So let's apply Newton second law on our mass. Sorry, it will be the same for this mass, okay? In this case, the tension will be along on this way. We are denoting as TR, okay? Again, because of this inclined plane and this angle, you have a two component of weight here, and also you have a normal force like this, okay? So let's go with the first one, and the left. You don't have any motion along the y-axis, so you don't need to know the you are not interested in the forces in y direction in the first step, okay? So we are only interested in the forces in x direction for both masses, okay? In x direction for the mass on the left, you have a TL, right? Along this way, let's say this positive, and you have a sine component along the x direction, sine component of your weight vector here, right? Vector weight quantity here. It will be ml g sine theta l, okay? This will be equal to 0. Why? And because your object are not slight, okay? And which means your system is at equilibrium, okay? So for this mass, the mass on the right will be similar thing. You have a forces because of weight on this way. This is mr, the mass of the right mass, times g, times again sine theta r now, this angle here, okay, minus tr, the tension on this rope, okay, again will be equal to 0. Now, if the masses of string and the pulley, this one pulley, are negligible and there is no friction, as said in the question, there is no friction in our system, then the tension in the rope must be same to the entire string. So in this case, TL will be equal to TR. You know, there's concept from the high school. If your masses of string and the pulley are negligible and there is no friction in the system, and you have as a single rope like this, so tension in the rope in both sides must be same, okay? So in this case, if you add these two equations like this, TL will be equal to T, right? TI will be equal to T. These two T tension will cancel each other, and the light and the last step you have this one, MRG sine theta R minus MLG sine theta L will be equal to 0. From here, if you compare the mass of the right side and the mass of the left side, will be like this, sine theta L over sine theta R. From here, your ratio will be this one, mainly, or you can write down like this, and R will be approximately 2 ml, right? Question? Next one. And you have a setup like this. We are calling this setup, this toy actually, a tether ball. In this tether ball, your rope is in 1.55 meter length, and this rope is struck so that it goes into a circular motion in horizontal plane, with rope making a 15, there's theta here, 15 degree, okay, 15 degree, and the length here given as 1.55 meters, and you will find this VT, velocity of this, sorry, the speed of this ball here, okay? And you can easily see that, and your system is in 3 dimension, but your object is moving in 2 dimension, XY, in XY plane, okay? So this is a kind of problem combining Newton's second law and the circular motion. In this, the force in this question generate a circular motion on the ball, okay? So first of all, again, as I said in the previous question, we should do a free body diagram. In this question, our object is this ball here, okay? This one, let's say here, this one, okay? And you know, it has a mass, so along the downward, it should have a weight force like this, okay? Also, there is a tension because of this rope, right? There are only 2 forces on this ball. One is tension because of this rope, and one is weight because of it is mass, okay? And then vertical component of the ball's acceleration is 0. Why? Because there is no, as I said, as I shown here, there is no motion along the y direction. Your motion is in xy plane. Sorry, there is no motion along the z direction. Okay, so and from the Newton's second law, we know that the vertical component of the tension force pulling the ball up must cancel gravitation force pulling the ball down. Of course, again, like in the previous question, this tension has an angle with the horizontal. So in this case, this tension has 2 components. One is this one is this one. If your object has a only motion in horizontal way, these 2 forces, this one, tensions, this component, and this one, the weight of your object, must cancel each other, okay? So in this case, the vertical component will be T sine theta, right? And what about this one? The horizontal component will be T cosine theta, right? So in this case, weight of your object must be equal this one, T sine theta, okay? This one. And then applying Newton's second law in the horizontal direction, and we know this is a circular motion, and this force will generate a horizontal motion. Actually, this force is F net is equal to the cosine component of the T tension will be equal to this circular motion equation, right? M times mass of your object times velocity square over this one, radius of your circular motion path, okay? So in this case, you will find this radius here, right? From the trigonometry, you can easily know that this hypotenuse here is L. L is when you multiply L with cosine theta, you will get this R here, right? So in this case, your R will be equal to 1.55 meter cosine theta, okay? So now let's stop here. You have three equations. One is weight is equal to T sine theta. The other one, the horizontal component of the tension generates a circular motion. Second equation here, this one. Also, you know the radius of your circular motion will be equal to 1.55 meter cosine theta. Okay. Now you will combine all this. You will combine. So you will solve this equation for v here because you want to find the ball speed, right? So in this case, if you rearrange this equation for speed here, you will get this one, okay? Tr cosine theta over m, and take the root here. And what is t here? T here, mgr cosine theta, okay? And and you can get the t from here. T will be equal to weight over sine theta. Also weight, you know, mg, right? So when you arrange this equation, when you put the t and r here, okay, you will get this equation. And cosine over sine, you know, 1 over tangent theta, right? Here, gr over tangent theta. And then you will only put the numbers here, and g is a constant here, and r here, 1.55 meter cosine. Cosine is, your theta is 15 degree, and tangent 15. From here, you will get positive or negative 8.36 meter per second. What does positive or negative? And in this question, we are only interested in the scalar thing, right? So we don't know ball's direction in this question. Your ball going on this way, clockwise, or your ball can go counterclockwise. Okay, so your speed can be in both directions. So that's why we are using both plus and minus signs here, okay? And in 5 minutes, this class will shut down, and you know, after shutdown, please rejoin the class again, okay? So let's go with this question. And you are lowering two boxes, one on the top of the other and down the ramp shown in this figure. And you are pulling on a rope parallel to surface of the ramp. Both boxes move together at a constant speed. What does it mean? Constant speed.
No acceleration.
Yes?
No acceleration.
No acceleration, right? Acceleration is 0 if your speed is constant or your velocity is constant, your acceleration will be 0. Nice. And the coefficient of kinetic friction between the ramp and lower box is 0.444, and the coefficient of static friction between the two boxes is 0.8. So there's a, of course, you can easily see that there's a difference between the kinetic and static friction, right? Kinetic and static friction. If you look deeply, the kinetic friction coefficient between this surface and this mass, and the static coefficient friction between two masses here, okay? So first of all, we should know definition of the static and kinetic friction coefficient. And then in part A, what force do you need to exert to accomplish this? If you want to make such kind of motion, what force do you need to exert on your system for part A? For part B, what are the magnitude and the direction of the friction force on the upper box? So first of all, as I said, what is kinetic and static friction? Static friction is what keeps the box from moving without being pushed, and it must be overcome with a sufficient opposing force before the box will move. Okay, this static friction actually protect the box from sliding. Okay, is a kinetic friction. In the case of kinetic friction, also referred as a dynamic friction, is the force that resists the relative movement of the surface once they are in motion. Here is important. They are in motion. If your object in motion, you should talk about kinetic friction. Okay? So now I think you know the difference between these two terms. And then what will do in this step? Of course, you will draw free body diagram, and we will draw free body diagram for these two masses. We will assume as a one mass, okay? Also, because there is a motion between this inclined plane and this mass system. Also we have a static friction, right? There's actually the forces between these two masses. So we should draw free body diagram only for these masses. Okay, again, we can draw free body diagram. Before the free body diagram, we can show our axis like this. This will be your horizontal axis, and this will be your, this will be your vertical axis. And of course, you have a mg like this, right? Weight, and here's a tension because of this work. Also, there's a normal force. Okay, will be similar with the previous question actually. So here your free body diagram. This one the for two masses system. Okay, and this one is the free body diagram